Imagine a dataset of sequential points jumping up and down erratically over time, looking exactly like the daily fluctuations of a major stock index. We feed this data into a sophisticated neural network. The model analyzes the history, identifies a trajectory, and predicts a confident upward trend. But when the live data arrives, it completely misses the sudden, violent crash. No matter how deep the neural network or how vast the computing power, not all sequential data contains a learnable signal. Modern forecasting architectures frequently fail because they mistake the accumulation of random noise for a genuine underlying structural pattern. Quantifying the degree of randomness in a dataset allows researchers to allocate resources toward models that actually have a signal to learn, rather than those effectively chasing static. To understand why these models fail, we have to establish the baseline of pure randomness. Imagine a simple coin toss. We record every heads as a positive one and every tails as a negative one. This is a plot showing those independent coin tosses over time. Each result is plotted sequentially, locking in at either positive or negative one. Because the coin has no memory of the previous flips, the probability of heads or tails remains exactly 50% for every single toss. Over time, these results average out to exactly 0. This system, where the mean remains constant and every point is completely independent, is called white noise. Notice the boundaries of the data. The spread of the outcomes remains tightly locked between 1 and -1, never widening or contracting as time moves forward. The variance is constant and securely bounded. In a strict white noise environment, yesterday's result gives you absolutely zero information about tomorrow's result. Therefore, the mathematically optimal prediction for the next data point is always simply the mean. Datasets in finance and nature rarely look like a flat band of static. They have memory, chaos that builds upon itself. Consider the classic drunkard's walk analogy. A person takes a step in a random direction. Their next step does not start back at the origin. It originates from the exact spot they just landed on. This chart shows a random walk, which maps perfectly to that analogy. Today's value equals yesterday's value, plus a new burst of white noise. The chaos is now cumulative. Because each random shock is added to the last, the boundaries are no longer flat. The variance of a random walk increases linearly with time, meaning the range of possible outcomes grows wider as the sequence progresses. This accumulated randomness creates a powerful visual illusion. If we format this wandering line with green and red bars, it perfectly resembles a tradable asset. It looks like it has momentum, support levels, and structural trends. That drifting shape is exactly what tricks human psychology and complex machine learning algorithms. They analyze the drift and extract what they calculate is a forecastable signal, when in reality, they are looking at a stack of random shocks. When you train a deep learning algorithm on random walk data, it eagerly gets to work, optimizing its weights and biases to reduce error. The model bends and twists to map every peak and valley in the training set. It memorizes the accumulated noise, mistaking the historical drift for a deep, repeating structural pattern. Then you deploy it on live data. The moment the noise resets and takes a new random step, the model's complex projection wildly diverges from reality. It overfit the specific history of the noise, rather than learning a generalizable law. In financial markets, this phenomenon is formalized in the efficient markets hypothesis, developed extensively by economist Eugene Fama. The theory states that in a highly liquid market, all known public and private information is already instantly priced in. Therefore, any future price movement is driven exclusively by new, unpredictable information, which arrives as white noise. If price movements follow a random walk, then historical patterns offer no predictive edge for the next step. This makes fitting complex regression curves to past price action a struggle against the very math of the system. This chart maps the naive forecast against our random walk. Instead of calculating momentum or cyclical trends, the naive model makes one strict assumption: tomorrow's value will exactly equal today's value. By simply carrying forward the last known data point, the naive forecast minimizes error over time. In highly efficient systems, complex modeling is a trap. The simplest assumption proves mathematically optimal. We can prove exactly how slight the mathematical difference is between pure noise and a deceptive trend using a few lines of Python. First, we generate a sequence of numbers by sampling independent points from a standard normal distribution, setting the mean to 0 and the variance to 1. This creates our raw white noise. Next, we apply a single mathematical transformation, a cumulative sum or cum sum, to that exact same array of noise. The cumulative sum function takes step 1 and adds it to step 2, then takes that result and adds it to step 3. It literally injects memory into the system, forcing each new data point to build directly on the position of the last. This dual-panel plot reveals the result. The top panel displays the raw white noise, erratic, tightly bounded, and visibly random. The bottom panel displays the cumulative sum, a smooth, drifting line that resembles a macroeconomic trend. Both of these plots are derived from the exact same underlying array of random numbers. One basic mathematical operation is all it takes to transform a static band of pure noise into a deceptive, trending structure that actively sabotages predictive algorithms. Data science faces a structural boundary. No amount of optimization or model iteration can extract a signal from pure randomness. A strict interpretation of the efficient markets hypothesis suggests no one can consistently beat the average. Yet there are active traders and investors who consistently generate returns that dwarf the overall market. These rare exceptions demonstrate that markets are not perfectly efficient at all times. Periodic bouts of excessive optimism or heavy pessimism drive prices away from fair value, creating narrow, temporary windows of true signal amid the noise. But if you point an unmodified deep learning architecture at a standard financial time series, the sheer volume of random drift will overwhelm those rare moments of efficiency. The model will optimize for the accumulated noise and completely miss the underlying signal. For quantitative analysts evaluating sequential data, the priority is not building a more complex neural network to handle the volatility. Before spinning up a single compute cluster or defining a model architecture, you must first mathematically prove whether the dataset actually contains a signal, or if you are simply staring at a random walk, pretending to have memory.